as Dom pointed out, I will be talking today about reactive crystallization and optimizing this using a slew of METTLER process analytical tools. So let's jump right into the material that we're crystallizing. We're going to talk about a highly insoluble energetic material, specifically 2,6-diamino-3,5-dinitropyrazine 1-oxide. But from now on, I'm just going to refer to that as LM105. So it was a material designation discovered in Lawrence Livermore National Labs. It was the 105th energetic material they identified. That was developed by Phil Pagoria at Livermore. It's an insensitive high energetic material. So that may sound a bit like an oxymoron, like jumbo shrimp, or, but it's actually, for its application, it's one of those things that has a lot of energy, but you don't want it to go off unless you want it to go off. So it's a material that they've been working on for a number of years. The original synthesis that we're going to start with today was synthesized a 4-step process, and with the last 3 steps involving energetic starting materials or products. So that's less than ideal, but that's what we had to work with. And the last step to form LM105, it proceeds by a slurry-to-slurry oxidation. So not only is the product highly insoluble, but so is the starting material. So here's some chemistry. I thought everybody in there would like to see this. So this step right here is the only non-energetic step. It's basically just make the methoxylation of the pyrazine to then we then put the nitro groups on, and once the nitro groups are on, we're essentially energetic materials. So this one has an energetic product, energetic starting material, energetic product. This material right here is amino-nitropyrazine, so they gave it this nice moniker ANPZ. So this is the step we're going to talk about here today. It's a heterogeneous reaction, and you might have noticed that a lot of the reagents used in the synthesis are less than ideal. So yes, we're doing a nitration in 20% oleum, which is solid sulfur trioxide dissolved in sulfuric acid. It's an interesting solvent system. The ammonia, the amination isn't too bad, other than that you get these crystallized out solid material that isn't very fun to play with. And just to cap things off, let's go with the oxidation. Why not use trifluoroacetic acid as our solvent and form the per-acid and do our N-oxide formation? So a lot of fun chemistry. So here's sort of what's happening. It's a slurry-to-slurry reaction. We have our product, our starting material ANPZ. It's a solid with only slight solubility, so very little here, the liquid phase. Then we have our reaction where we oxidize it and make our little bit of LM105 in solution, which then rapidly crystallizes out, so that reactive crystallization there. One of the nice things about this is this is PVM images of the starting material, the TFA slurry. You can see it looks like snow, just really small particles. And when you do the oxidation, you end up making these relatively large cubic LM105. And that morphology is something they really liked. So as anybody who's making material realizes for like either API or energetic materials or any sort of the final material of interest, they don't really care about this until it goes into a formulation. So you're constantly at the whim of the formulators to tell you what particle size and what properties they want and what form. So same thing in energetic materials. The formulators want this blocky cubic material because it was ideal for the formulation this material was being placed in. When they went to scale this up, here's a trace of a 50-liter reactor scale up of this oxidation. So unfortunately, it looks kind of crazy, and that's partially because we're in jacket control. This was being run without an elegant control system. So your PID was your operator. His job was to sort of anticipate where he thought the TR was going and sort of, heat it up really quick to get TR up where I wanted it, cool it back down, okay, have a good driving force before I start dosing my first dose of 50% hydrogen peroxide. And when we did that, not much happened, minimum exotherm, and then started heating it up, and then it kind of got away from him. And it ramped up to the boiling point of the solvent system. So this reactor had refluxing TAFA, and there was not a good day. But it kind of got it back under control, and he said, well, you know, I've gone this far, let's dose the second hydrogen peroxide dose, and they did. Not too much heat comes out, and oddly enough, they got pretty decent LM105 out of it. Unfortunately, you probably don't want to do this. I mean, 50 liters was too big to have this sort of event happen. You much rather not have a process that involves refluxing TFA. So we need to do some process understanding to say what happened here, but also where are we in the reaction? What kind of crystallization events are we happening here? So grabbed it, took it into the lab. Here's some RC1 data showing heat flow calorimetry. So here, we have a lot better jacket control. So we've taken the duty of being a PID away from the individual and given it back to the computer, which was beneficial. So we were able to dose our hydrogen peroxide. We see a little bit of heat flow during that, formation of the peracid, a little bit of oxidation. Baseline, a little bit of heat, doesn't quite go back to baseline, but then when we ramp, and we did the ramp slow, and we made it proportional to TR so we could get an idea of the heat flow during the ramp, which in heat flow calorimetry, temperature ramps can be a little tricky. There are some ways of getting around it, and in this case here, it was a slow ramp coupled with making the heat flow integration proportional to TR. So you can see here as we're heating, jacket's leading like it's supposed to, and then towards the end, all of a sudden it kind of crosses over and we start cooling. So we're saying, hey, there's a reaction taking place on this ramp. The question is, what reaction? Is that our desired, you know, oxidation and forming our product? Or is that sort of the thing that led to that runaway that we saw at the 50 liter? You know, we see a nice amount of heat coming out there, and then second dose, not too much heat, and we're done. Along each one of these stars, we were pulling samples for HPLC to track our conversion. Let's go back and look at that heat flow. So first question is the decomposition of hydrogen peroxide and TFA at these temperatures? So let's run some blanks. So first thing we did was, we know there's a reaction taking place. Is it trifluoroacetic acid and hydrogen peroxide kind of doing something? Well, this blank run here indicates no, it's not. You can see as we do the temperature ramp, it's exactly what a temperature ramp heating reactor contents with no reaction should look like. The jacket's leading and TR is just maintaining a nice constant delta T, and then we get it under control, lower delta T to maintain that temperature, and everything's happy. Now we run that same reaction with ANPZ in there, and we see that we have that crossover and reaction taking place at the end where the jacket's actually cooling once we reach the 50 degrees. So from here we can say, okay, the reaction, this seems to be consistent with our desired oxidation. So we have the desired oxidation, 50 degrees, why did that run away on a large scale? So this is where I use the obligatory METTLER slides for how an FBRM works. Stop me if you've heard this one. Here's the cutaway for our FBRM. We got a beam splitter, some rotating optics, and it's all done with lasers. So lasers come down, rotate around, focus the beam right there at the end of the window, and then any sort of backscattering comes back at the laser source, and we get detection fiber, we can see what's happening. So that thing's running around in circles really fast, meters per second. And as it's running, that is then looking across, and it's backscattering. So FBRM is essentially just backscattering on the laser light. So as the laser is going across and it hits a particle and backscatters, that comes back to our probe, and we can say, hey, we see chord lengths. We take those chord lengths, that gives some, thousands, put them into our buckets, and we can get sort of a chord length distribution, which is sort of a stand-in for particle size distribution real time. Now, if you remember the PVM images we showed earlier about the ANPZ and the LM105, ANPZ is fine material, whereas LM105 is large blocky material. So now if we look at FBRM data from those runs, here we see that, we got all our ANPZ in solution, so our counts are the fines, 0 to 10 microns, shoot right up because there's a whole bunch of solids in there. And then we add our hydrogen peroxide, and it sort of kind of drops from dilution, and then it's slowly going down. And then we have the section where we heated, and you see a rapid decrease in the fines. And meanwhile, the mean no weight is increasing, indicating that we're forming our LM105. And that's climbing up. And then you see the second dose of hydrogen peroxide and you say, well, you really didn't need that much in there because we didn't really make much more material and you were almost there anyway. So one is we can probably cut back on the hydrogen peroxide we're using. And two, that reaction during the ramp is actually driving the reaction. Now, unfortunately, when you're scaling this up and you've got a larger reactor, you really don't want to have two things happening while you're trying to heat it up. You know, one, we're trying to put heat into the system, and then you have to magically figure out when the heat's going to come out and basically throttle back so you don't overshoot your control point, which is what happened on the 50 liter. So the idea is, well, if most of the reaction's taking place during the ramp, and right here we just have a large accumulation term. All our hydrogen peroxide is waiting to, one, drive ANPZ into solution so it can react, and two, to really kick off the reaction. So why are we doing it at a 2-temperature regime? In fact, here's looking at the thermal conversion. You see most of the heat jumps up here. This is a zoom in on the temperature. So this is the first dose. ANPZ is going down, LM105 is going up. Once you ramp, you get a big step and increase. And then you can see also the LM105 does not really increase after that second dose of hydrogen peroxide, much like what we saw with the FBRM trend. So because these two different materials, starting material and the product, have such a different particle size, we're actually able to use the FBRM as an in situ probe to track their concentration. This could also be done with Raman, but at the time we had the FBRM, and because the materials were so dissimilar in their morphology and particle size, it worked out really well to track the reaction with FBRM. So back to that temperature. What temperature do we want to run this at? So we started looking at, instead of dosing it at 30 and then ramping to 50, can we just dose it at a lower temperature and get the reaction to take place without a temperature ramp? So basically keep it in there so we don't have this accumulation. Now, of course, in order to really balance this, we're going to need to balance our dose rate with the mass transfer rate, because even at the right temperature where the reaction will take place, if you dose it too fast, you'll have accumulation. So here's a series of RC1 runs that we did. One where we dosed it all at once at 45 degrees, and we saw we got quite a bit of heat, and then it just kind of trickles on down. Then this dosing profile here is the same dosing profile for 40, 45, and 60. You can see that at 40, it's kind of slow. So same amount of heat comes out at 45, though it seems to end a little faster. And at 60, this is starting to look a little bit more like that 50-liter reaction we ran, where it kind of ran away. And we see here that at 60, when we dose it, we get a substantial larger amount of energy coming out. The energy produced in the RC1 is, as measured, is the sum of all the reactions taking place. If this were the same reaction, we should have the total integral amount of heat should be the same. But at 60 degrees, we see that the heat flow is dramatically increased, indicating we have additional reactions taking place. And in fact, when we tested at the end, we had very little peroxide left, indicating that we'd actually decomposed a fair amount at 60 degrees. So here's some looking at the conversion rates. This is offline HPLC data converted into actual molar conversion percentage, shown here on the left axis. And this over here is the equivalence of hydrogen peroxide dosed. And this is different temperatures. So we can see the ANPZ going down, LM105 going up for each case. And at around 40 to 45 degrees, this green one here, we're able to match the production of our LM105 with the hydrogen peroxide coming in. That way we realize that if we're at that addition rate of around 2 hours, or 3 hours, or a little over 3.5 hours, at scale, should allow us to keep up with the mass transfer and not have any real accumulation of the hydrogen peroxide, rendering it a little safer process. That's great, but one of the biggest problem here is, see how we're kind of capped at 90? Sometimes we get to 93, you know. Sometimes we always had ANPZ left over, and that's because of the slurry-to-slurry transformation. We were getting inclusion of our starting material in our product, which unfortunately That's not what we want. So are we successful? Are we there yet? Well, we can dose hydrogen peroxide at 40 to 45, maintain the reaction rate balance with our mass transfer. So that's great. Minimize accumulation, safer process. Always want a safe process when you're making explosives. Unfortunately, we still have that 7 to 10% ANPZ. And not only is that unfortunate because it hits your yield, but there's a stability issue in the formulation with leftover starting material. So that's sort of a double whammy right there. Yeah, this is kind of going to start impacting the material, and it may not move forward because it's got a black eye. People look at the stability. They say it's not stable. Let's go on to the next material. When we said, whoa, it's actually, we did some series of DSC compatibility tests, and we showed that thermal stability was dramatically impacted by residual ANPZ. So we said, no, the material's great. You just got to get rid of that. And like I mentioned before, we still have 3 steps that involve an energetic material as a starting material or product, which, again, you rather not have multiple tanks full of energetic materials. We'd like to kind of minimize that. So, as is always the case, the chemists came and saved the day. They came up with a new process. So this new process would allow for only the last step to be energetic. So they basically built the molecule and put the nitros on last. And that basically gave us LM105 as a product. And it's very high purity. Because LM105 was made in the reaction, it was a solution as a mixed acid nitration. You got a complete conversion to your product, and then you could quench it in water and then get your product out at a very high purity. Of course, nothing's free in this world, and we got high purity, safe process that resulted in a needle morphology in the quench. So now the formulators are mad, saying, we really like that blocky material you guys used to make. If you could just make that. So, all right, where are we now? We're not there yet. So right now we have the desired morphology with undesired purity. We have desired purity, but with undesired morphology. So this is that blocky, cubey, Route 1 ANPZ produced LM105. I really like that. This is the silty looking fine material that we'd quench out of water. They didn't like that. So now the question is, can we make this look like that? And of course we can. We just give some time, we'll get there. So how do we fix this? They want large particles. So luckily for us, they said, if you could make it bigger, that's great. Just there's no limit to the size, but we need to have at least something over 50 microns. So can you guys, and also we've made a substantial amount of that fine silty material, high purity, but really can't use it for anything yet. Can you come up with a way of processing that and then recrystallizing it? So we can get that desired purity, particle size distribution, and morphology. And they tried to take the material from the first route and try to clean it up, and they couldn't do it. It's highly insoluble, and every time they precipitated it out, they still had the ANPZ. So trying to re-oxidize the material, you could increase it slightly, but it still didn't change the fact that you still had 3 energetic steps. So let's see if we can get a low aspect ratio, lower, something around 2, 2.5, large particles, and if it can look like this, that'd be great. All right, well, we need to go find a recrystallization method. And this probably should not involve too much seeding. So again, not so much a regulatory issue about having to have a GMP seed, but more around the idea that you don't really want to be shoveling in or somehow transferring the energetic materials into a reactor to kick off that crystallization. So ideally, you'd like it to be self-seeding. So also, we have plenty of anti-solvent. I mean, pretty much anything's an anti-solvent thing. Problem is we need to identify a good solvent. And, combination of anti-solvent and cooling to kind of get us where we wanted to be. So we could generate that seed bed in situ. Oh, and like I said, we have a whole bunch of this material we need to convert over, and we have some 200-gallon scale material. So can you guys make sure that it's also scalable to get the same particle size and morphology when you scale it up? Okay. So this is the sort of the bulk material as it comes out after the crystallization. You can see very small materials here, especially when you get it across that axis, and then the majority of it's sitting at a well below 50 for a D90. D50 is hanging around 20. So we need to make that much larger. So let's go find a solvent system first of all. Okay. What can we screen in? So Crystal 16 is great for screening solvents and solubility. So we jumped into that first. And we kind of only had this type of solvents to pick from. Sulfolane, DMF, NMP, DMSO. You can see these things here, I mean, in fact, like DMAC wouldn't even touch it. You need a high temperature and a fair amount of volumes to even get it into this. Anti-solvents, water, acetonitrile, alcohol, so those were all promising. So what we wanted to do is find some sort of maybe cooling crystallization that we would identify a metastable zone, and then we take polarized light microscopy of the solids to see, hey, after we heated it up and cooled it down in the solvent system, what kind of morphology did we get? So here's the DMSO and sulfolane results. We were able to get it into solution and get it back out again, but if anything, we've made it worse. These are not exactly what I'd call a low aspect ratio particle, and definitely not blocky. So those ones were quickly eliminated. I'm only showing a few of the slides. We looked at sulfolane and DMSO through all the anti-solvents as well. But no matter what we did, it always came out looking this way. DMF looked a little promising. It looks like it was slightly thickening up a bit with a little bit more water. And that quickly, kind of hinted at that, a large amount of anti-solvent at the higher temperatures may give us the right morphology. And when we went to NMP, that really kind of lit up. So with about 5% water, you still have needles, but they're thicker than they were before the DMSO system. But then 10% and 15%, now we're talking. We're getting some material that is got some sort of aspect ratios that they are going to be interested in the formulation. And here's some more. We looked at different solvent systems, ran all these on the Crystal 16, and in fact, here are the solubility curves. And this is good. So we need the water or we're going to have a terrible yield. Unfortunately, if you add too much water too early, it'll crash out. So we were trying to take this data here and design a crystallization process map that'll get us where we want to be. So at the end of the day, we want to be down here. Everything out of solution with a lot of water. But how do we do it so we don't have everything out as needles? So this is what we did. We first came up with some solubility curves now as a function of anti-solvent at different temperatures. So here we have the 90 degrees solubility. We get quite a bit of water in there. Quite a bit of material in there before adding the water. And then when we cool it down, we're going to, most of that material back out. So the idea is we needed, I'm not presenting it here, but one of the things we found out is the stability of that product, L105, it is not very good at high pHs. And NMP, as you heat it, NMP is a very weak base, but it's a base nonetheless. So we found that long-term stability, if it was held for a number of hours at 100% NMP, you would actually get some sort of decomposition and degradation of the product. So we found that once we put in about 5% water, that completely shut down and it was stable at over 90 degrees for over 4 days with no degradation. So that's why this is our starting point for this crystallization. So we start there, then we add our anti-solvent to get it out of that steep section of the solubility curve. We found that if we tried to cool, it would quickly secondary nucleate and get a lot of small fine particles, whereas if we could add a little bit of water very slowly, we would generate the seed that we wanted with allowing it to grow. And then we'd add more water much faster and then cool it and get us to our endpoint. So this is what we have here. We heat everything in NMP with a little bit of water, heat it up to 97 degrees to get everything in dissolution, so it's now solubilized. Then we'd cool it down to 90. Basically, if we go back here on the curve, what we're doing is we're going over here and then dropping the temperature to drop just below the solubility curve. So now we have some supersaturation built up. So as we start to add the water, it would start to very slowly here, it would crash out the seed bed that we wanted. And so we take it from 5 weight percent to 7.5 weight percent. And then we could rapidly add the rest of the water, maintain that morphology we want, and then cool right after the end of that with no hold point, and isolate over 90% in the morphology we want. So here is the we ran this at 2 liters in the RC1. Here's our temperature profiles and the FBRM trends as well as the water dose. So initially, we start dosing and we see the particle size start coming up, and we're getting some growth as we're dosing in the second charge of water. Actually, a fair amount of growth as we cool, and then once everything's out of solution, we isolate. So here is our setup. This is the 2-liter RC1 with our PVM or an FBRM probes in there, dosing our anti-solvent. And this is the PVM images from the 2-liter while we were recrystallizing, indicating that we were getting our large blocky material. So from that, we see the particle size distribution of the incoming material versus the outgoing material from the 2-liter campaign. And we see here that mission accomplished. We got much larger particles, really shut down the fines, bumped those up to close to over about 1020, and then the majority of the material well over 100 microns. There was a substantial amount of work that was done after this to identify the optimum feed locations and dosing rates for scale. Involved quite a bit of CFD work and everything else. I won't get into that here in this talk, but we basically were then able to show this material here that we isolated at the 2-liter from this material here could give us the right morphology and particle size. We got our particle size distribution, the correct morphology, and purity. One of the things I have to say that we're very happy about is that LM105 does not have a polymorph issue. That is not always the case in energetics, and it's never the case in pharma. So that, I have to say, did simplify the project substantially. We weren't concerned about form, though we did check with powder X-ray at every step. So this material here recently, actually, we did take this up to 200-gallon scale and at our customer's location, transferred the process, ran 3 batches, and this is the overlay of all 3 of those particle size distributions. So like I said, there was a fair amount of work to go from the 2-liter to here that's not covered in the slide, but needless to say, the solvent system met the goals. So at that point, we have successfully scaled the material to the correct morphology. So this was just a quick run through on what we did with the starting reactive crystallization. We solved that problem only to find new problems. We identified that if we could maintain the mass transfer limitations with the dosing rate, we could overcome that and make material that was in a safe process, as safe as making energetics can be. But unfortunately, that starting material inclusion led to issues that required us to get new chemistry and more, but that resulted in wrong morphology. And but that wasn't a stopping point. We were able to then design that recrystallization that could get us back on track. And currently, the material is moving forward to potentially bigger and better things. So with that, I'll open it to questions.